Yes, it's really nice to have you all here, and the mayor is correct in saying you're the ones that are going to have to deal with what's going on in the next few years and to pay attention to be able to make the right planning choices for infrastructure and development and how you use your resources. We're going to look a little bit more specifically at climate change in Sonoma County, and yes, it's probably going to rain more in the future too. So we're going to look at a few different applications of how climate change is having impacts currently. Yes, we're in the midst of it still, and how it may potentially change in the future. There's various, our motivation for the work that we've done in Sonoma County is local water agencies, and we've had projects with the Sonoma County Water Agency and the North Bay Watershed Association, as well as DWR and various other entities that are interested in the North Bay. They're seeking assistance from us to address the hydrologic and environmental impacts to future climates. They need science-based information to plan for management of landscapes and water resources in the face of climate change, and this happens to be a new mandate for Sonoma County Water Agency in the light of biologic opinions. Our goal is to translate climate change to hydrologic response and environmental impact. This requires taking the stuff that you get from global climate models and downscaling them to a regional basis. Requires an approach to simulate hydrology from available information. And we hope to somewhat reduce the huge uncertainty that's inherent in future projections by rigorously adding deterministic processes, things we know aren't changing. Topography is not going to be changing, hopefully. Solar radiation is not going to be changing. There are things that we actually have a control on that have less uncertainty in the future. This is what we typically see when we think about this. Well, today we're thinking about tornadoes in the Midwest, but this is typically the global climate change view that people have. And maybe it's a little bit more regional for some people. They're getting hotter in the Southwest, for example. So we have to go from the global climate change down to Sonoma County. And how do we get there? The projection for air temperature, the deviation from the mean, is shown on the left hand. Do I have a? Oh, probably not. Okay. Is shown on the left hand, and that is the mean global change. It only shows an increase over the mean, the base period of 1951 to 1980, of about 0.6 degrees. That's globally. If you look at the variation, however, over the globe, you can see that some places have gotten as high as 7 degrees warmer over that period of time. And this is in February 1910 to January 2010 to 2011. So this is the deviation from the mean ranged over the entire globe, and you can see lots and lots of variation. You can see that in 2010, the East Coast had it was very warm, whereas the West Coast was cooler. Well, it's every year it seems to be a little different. Year before that it was snowing in DC, or last year it was snowing in DC, and it was warm in Canada when we had the Olympics. So there's lots of variation, and the whole point is about taking that global mean and applying it to where you're experiencing change. This is the downscaling problem. The global climate models work at a global basis so that they result in 12 grid cells for the state of California. So we have to take those 12 grid cells, that's about a half a grid cell for Sonoma County, and we have to bring that down to where we can actually look at climate the way that we currently see it. So I'm going to talk about some downscaling methodology and rationale for fine-scale modeling, the water balance modeling that we do to translate climate change into environmental impact, and I'm going to give you 3 examples in Sonoma County, one for water availability, one for habitat impacts, and one that describes a couple of impacts to viticulture. That was my agricultural thing that was the topic today. Fine-scale application, when I talk about fine-scale, I'm talking about grid cells of 270 meters. So that's about a 17-acre grid cell. We're bringing it down from 250 square kilometers to 270 square meters. And that spatial scale is something that people that manage habitats and water resources can actually think about vegetation distribution in local environments, whether you've got snowmelt on north or south-facing slopes, basin scale, future runoff. There's lots of processes that occur at that fine scale. So we're going from the large scale to a fine scale, and the first step is typically done by climatologists. We have our USGS climatologists that have used a very rigorous analysis called constructed analogs, which then takes you from the 275 square kilometers down to 12 kilometers. These are the kind of data that are typically available online. You can go to a website that has multiple scenarios available, and you can get those at 12 kilometers. So we start with the 12-kilometer analysis, and then there's a whole number of scenarios that are available. The ones that we're currently working with are a medium-high emission scenario, A2. That assumes that we don't get our act together, or that we pretty much stay business as usual. And then we also use a B1, which assumes that we do get our act together, which so far hasn't been the case. And then we also have two models. These two models were selected specifically because they represent the sort of quadrants in California that are predicted amongst all of the ensemble predictions. So there's the warm wet, the warm dry, the cool wet, the cool dry. These two represent, so that's what these two represent. I will highlight the GFDL-A2 because it's more realistic, and I will show you that. The PCM is less sensitive to greenhouse gas forcings, so has more inherent uncertainty in it. This is a suite of scenarios, and you can see that the colored lines are the scenarios. These were developed in 2000. These are run out to the future, and this is the fossil fuel emissions. So this is what are projected to go out through the future. This only shows through 2015, and the squares and the points are the actual measured emissions, so that you can see that the scenarios that were developed in 2000 have been overlain by the measurements, and we are currently over-predicting all of the scenarios. Those are the solid lines. So I have a tendency to go with the worst case at this point. If you run all of the multiple scenarios, you can see that there's not a lot of agreement amongst them. There's much more of a consensus on the top graph, which was air temperature. So typically all scenarios agree that we're going to be rising in air temperature. We've been seeing this for a number of decades now, although there is some disagreement on exactly how much. And both of the scenarios I'll show you do increase in air temperature. However, the precipitation is all over the place. Some days, sometimes you have precipitation in May, and sometimes you don't. So we'll have a scenario that shows an increase in precipitation and one that shows a decrease in precipitation. So once we get these scenarios, we then downscale them further. The upper box on the right-hand side is 12 kilometers, and these are three watersheds in the Sierra Nevada, just to show you sort of what the scale means to the topography. And the 12 kilometers we take down to 4 kilometers, which is the middle box. It does a little bit better job at describing the topography and certainly high elevation air temperatures. The reason we do it to 4 kilometers is because there is a national precipitation and air temperature database called PRISM. It's been developed by people at Oregon State University. It's very commonly used, and it's available at 4 kilometers historically back to 1895. Well, future climate scenarios aren't actual, they're not telling you exactly what the absolute temperature is. All they're doing is telling you what the trend is. So that you have to correct those. It's called bias correction. You have to correct it to make it so that at least today we'll start out in the same place. So we correct it to historical data from 1950 to 2000 so that the run-up in the future climate scenarios that doesn't have greenhouse gas forcings for that period of time, then those amounts match, so that when the greenhouse gas forcings are included in the model, then we at least start at the right place and go forward. So then from that point, then we take it down to our 270-meter grid size spacing for model application. Hello. That's done using this lovely equation. This is called a gradient inverse distance squared approach, and you've probably all heard of inverse distance squared, which means the closer you are to a point, the more highly it's weighted, so the more important it is, like if you're using station data. This imposes a regression for every day, for every month, for every grid cell that incorporates northing, easting, and elevation so that we can capture things like adiabatic lapse rates. We can capture storm tracks and things like that that are spatially obvious in the data, so that when we actually downscale from 12 kilometers down to 270 meters, in many cases we're actually improving the estimate of air temperature or precipitation. So then we take that data, we apply it to our watershed model. This is called the basin characterization model. It's a very simple water balance approach, deterministic approach that is grid-based. It's run in Fortran. It calculates in-place recharge or generated runoff, which means it doesn't actually route into streams and move water downstream. It's a monthly model for this application. We've also taken it to daily for a number of finer scale applications. It relies on an hourly solar radiation model that uses topographic shading and cloudiness so that you're getting differentiation between north and south facing slopes, for example. It also relies on vegetation density for evaluating potential evapotranspiration. It does snow accumulation and melt. It incorporates soils data. For Sonoma County, we have StatsGo data nationally, and where we have available, we have SurGo data, which is local county level mapped data. This is for hydraulic properties and depth that help us to determine soil storage, so how much water the soil can hold. Then geology is used. This is one of the few models that actually incorporates bedrock permeability, which would allow you to differentiate between recharge, groundwater recharge, and runoff, which is a very important thing for being able to optimize your water availability in many locations. Precipitation and air temperature then available using historical data sets or the future projections. So Sonoma County, and I've put the major highways on in red so that you know where you are, and the major river basins, Russian River Basin, the Laguna de Santa Rosa watershed, Napa and Sonoma valleys. And this is current climate in Sonoma County. This is 1971 through 2007. Precipitation's on the left, and you can see how you have higher precipitation on the coast, a little higher precipitation at higher elevations. Maximum air temperature definitely is higher in the valley and cooler on the coast. And minimum air temperature, it doesn't have as much of a spatial signature. There's a few places where it's a little cooler. And now this is the recent changes in climate. This is 1971 through 2007, but it is the trend over that period of time. For every grid cell, a regression was run through all the historical monthly data that tells you sort of what the direction of change has been over that period of time. And if you look at precipitation, there has actually been more increase in precipitation in Sonoma County. All the blue colors indicate an increase in precipitation. Maximum air temperature, however, is different. The green and blue colors are decreasing in maximum air temperature, and the warm colors are increasing in maximum air temperature. And I show you this not to say exactly how much or anything like that, but to illustrate that there are actually topographic and local controls that control how temperature is changing. So there are places that are more resilient to climate change. It's one of the implications of using fine scale modeling. We went to we actually did this analysis because a couple of years ago we went to a Laguna conference. It was a big conference we had, and there were two guys up there that were one was giving a presentation on wine grapes, and he said, "My vineyard's getting colder," and the guy in the audience said, "My vineyard's getting warmer." And Alan, he says, "I can show that. They're both correct." And so we show this kind of thing over time, and this has been true throughout the whole Sierra Nevada as well. There are places where adjacent basins actually have different kind of topographic controls that have had different changes in air temperature. Minimum air temperature, you see similar kind of things, whereas mostly it's increasing minimum air temperature. There are a couple of pockets that have a little bit more cooling trends. So now we use that kind of data and we can develop our model. This is the kind of geology that goes into this. We assign A bedrock permeability to these different units, where you have things like sandstone that has a high permeability, volcanics potentially have a lower permeability. So if you have a lower permeability, you're more likely to be runoff dominated. If a higher permeability, you'll be recharge dominated. So this is throughout the basin. You've got a lot of variability, and this is sort of an iterative process in calibrating this model. This is the soils data that we have, and this is an example of soil depth, and this also controls whether or not you have soil water storage and if the water can run off or the plants have it available for their use. Calibration is done locally using discharge measurements. This is just an example of one basin, the Maacama Creek Basin, which is in the eastern part of the Russian River Basin. And this shows, the top graph shows measured versus simulated for yearly data for this period of records, which is matching the total volumes within the basin. And the bottom graph is showing how well we match stream flow data, just to give you a little confidence in the kind of results that we show you. Okay, so the climate for Sonoma County for current and future conditions using 4 scenarios, and these sort of duplicate those plots I showed you earlier, where you have historical data in the black line, and then for the top graph, the future precipitation is all over the place. Well, for the most part, it either stays about the same or it declines at the end of the century, and there's lots of variability from decade to decade. These are averaged over decades. In all cases, in the bottom, all scenarios suggest that we're going to rise in air temperature for Sonoma County, and it's about, I can't read it, it's about 3 to 5 degrees, depending on which scenario you believe. Those kinds of numbers in runoff, now this is current runoff for the current period of record, and you can see places on the left-hand side that show lots of runoff. Those are the dark blue colors. The valleys show less runoff. They have deep soils. They soak up the water. They don't run off. And recharge is on the right-hand side, so there's a number of places where we actually have high recharge and low recharge. You can see the Russian River Valley actually just soaks up the water into the deep alluvium and doesn't recharge necessarily. We look at this next one is the change in runoff. Now this is the absolute change for the wet scenario on the left, and it actually has some increases in runoff, a lot of increases in runoff actually, about 50 to 100 millimeters per year per grid cell. On the right-hand side, the dry scenario shows a big decrease in runoff, except in a couple of places in the main channels. And this is the change in recharge. So we have similar kind of thing where the wet scenario has a little bit of an increase over most of it, and the dry scenario actually ranges in recharge, where recharge is not as sensitive to changes in climate as runoff is, and that's something that water managers ought to acknowledge, that there's big lags with recharge, and you can still, if you have really wet years, the groundwater storage will then be maintained over a longer period of time because it's not as flashy as runoff. It's not as difficult to manage in future climate. Other things that we're going to see in Sonoma County is a change in the seasonal timing of hydrologic processes. The historical, this is precipitation, evapotranspiration, and recharge and runoff, and this is just monthly averages, the difference between 1970 to 2000, which is the green line in each case, and then the end of the century, so that's 2071 through 2100. And in all cases, the seasonal precipitation influences are shorter. So we have less rainfall early in the season and less rainfall late in the season, so you're compressing your actual wet season. That translates into having lower recharge and runoff in the early part of the season and lower in the late part for all of these. Now for the wet scenario, you actually have a spike. You have a wetter mid-season. In the middle of winter, you have more water. Unfortunately, unless you can store that water, that's not going to do you much good. It also can fill up the soil and then just either run off or drain away, and it's not of much use unless that infrastructure is planned for ahead of time. Here's an example of future stream flow conditions for that one creek I showed you, Maacama Creek, and the The blue line is the historical, this is the cumulative probability of stream flow for all the different discharges. So the discharges represent the range of discharges through a season. And this is for, the current is the 30 years current, and that's the blue line. And the red line, the red dots are the wet scenario. And it shows that it doesn't change for most of the stream flow hydrograph, except at the very wet end, there's lots more very high flows, almost double high flows for that scenario. For the dry scenario, however, it's drier throughout the entire hydrograph. So throughout the entire season, you're likely to have drier conditions given this scenario. Another way to look at future conditions is drought. This is 3-year running average. Oftentimes, 3 years are what, if you have 3 dry years in a row, those are considered to be droughts for a lot of water resources applications, like that's how long reservoirs take to dry out. And so the blue line is historical, and the red and green are the 2 future scenarios. And the black dotted line is a relatively arbitrary line that's there to illustrate major droughts we've had in the past, and that includes, I don't actually have the last couple of years, but you have major droughts. So there were 4 major droughts over the last 90 years, and in the future, you can see that even though they may not be quite as extended, there are additional times those scenarios drop below that line. And the worst case is the multi-decade drought at the end of the season, at the end of this century for the GFDL A2 scenario. That's a way of looking at potential future drought conditions. And yes, it may rain in May, but you better hold on to that water because it's probably going to be a drought. Another thing that we can do to look at application of climate change is to look at demand. Now this is a climatic water deficit. It's the annual evaporative demand that exceeds available water. So basically it's potential evapotranspiration minus what the plants actually use. So it defines the deficit, what they would have used if they had it available. We calculate it using soil water storage. So if you have shallow soils, there never was that much water. You could have a whole bunch of rainfall, but the plants still only have what's available in the soil. And if you have deep soils, then there's lots of room for the plants to have available water so that they don't go under deficit. The graph on the right is a 1 year. It's a monthly calculation. We add it up and we have a cumulative value for the year. And it's distributed across where you can see the very high deficits in the Central Valley, very low deficits on the coast, and then a lot of variation in between associated with topography and soils and things like that. So if we look at a close-up on the left-hand side, this is in the South Bay where they have, you can see the north and south facing ridges, where the north-facing ridges actually have less deficit, so they're blue, and the south-facing ridges have more deficit, they have more radiation load. And you can see the corresponding on the right-hand side, and I can't actually show this, but on the right-hand side you can see corresponding oak woodlands, which are predominantly on north-facing slopes. And anybody who's driven down Highway 680 has seen that very obviously. In a droughty environment, this is something that stands out like a sore thumb in a lot of places. Well, something we rely on to develop a correlation of where certain species live with what their climatic water deficit requirements are. This is climatic water deficit for Sonoma County, and you can see certain places on the east side where you can see some north and south facing slopes, and you see a little more drought toward the east, and you see less drought toward the west, but you still see some of the slope issues here too. And then the river basins you can see have less deficit because they have more soil water storage. And this is the change in the future with the wet scenario. And the dark blue is the only places where you actually have a decrease in deficit. There aren't very many places, well, there's just a few cells in the bottom where you actually have a decrease in deficit with increases in precipitation, because the deficit is driven by the air temperature and the potential evapotranspiration. On the right-hand side, if there's not as much rain, there's going to be deficit. I'll show you how this actually plays out in terms of a species. So this is mapped locations of redwood forest in Sonoma County, all the little red dots. And what we did is that we took, for every grid cell where there was a mapped redwood forest, we took out the average annual current climatic water deficit. And we developed a cumulative probability. So that dark blue line on the right graph this is climatic water deficit along the bottom, and then it's just the cumulative probability of all of those cells that were mapped redwood forest. So this defines the bioclimatic envelope in which that species lives with regard to this particular parameter, water deficit. And keep in mind, this parameter incorporates all sorts of energy balance, water limitations in the soil, temperature, and rainfall. So it integrates a whole lot of drivers that dictate how well plants will grow. So for redwoods, they live over this entire range of climatic water deficit. A few of them live in the very wet part of it, and more, the ones in the very upper end, there's a few that are living at the edge of their environment. So if it gets drier, they're going to be the first to get it, right? The other colored lines are for those same grid cells, how those grid cells are going to change through time. So by the end of the century, only 20% of those grid cells still have suitable climatic water deficit that they can live in, suitable environment for them. So let's look close up at, this is the Russian River Valley. You can see the Russian River that heads on out to Jenner, and Guerneville's right in the middle of the map, right, that little hump right there. And the left-hand side is the suitable climatic water deficit now. This is what these trees have grown up in. This is what they know. This is where they could live. Now, they don't live in all these places. This is where they could live. And so you'll notice that actually a lot of them are living on some south-facing slopes. They're not living right on the coast. They're not living in the deep channel bottoms. It's actually too wet for them there. And on the right-hand side, this is the end of the climate. This is the end of the next century, and their suitable locations have moved to the coast, actually have moved into some of the channels, and they've moved to the north-facing slopes. Now, if we overlay where they currently live, and that's all the other colors, you can see that there are the lower 10% of their distribution. The ones that are living in the wet zone are in the blue, so there are certain places they're living. The ones that are living at the very edge of their environment are the red, so there's not very many of those, so they're the first to go. Now, as climate changes in the future, those yellow ones are going to turn red, and the blue ones are going to turn yellow, right? And a bunch of them are going to disappear. So we've gone down to about 20 to 30% of the original locations where they could live. Many of them turned red. So now those are living in the upper end of their suitable environment. But there's still a bunch of blue ones. Those didn't change. Those are resilient locations. Those have topographic shading. Those have deeper soils. Those are ones that if you're going to put all your eggs in a basket and manage for redwoods, you don't have to worry about those. You got to worry about, you don't want to worry about the red ones. There's probably nothing you can do about that. But you can worry about how to manage it by looking at the main portion of the population and say, what trees should we invest our time trying to manage? And if you want to look just a little closer up, we actually, at 270 meters, you can think about the location on the little hill right there, right outside of Gurnwood Park. You can realize that Armstrong Woods has had a big decline. It actually is living toward the upper edge of its range right now. So there's certain ways, if you're going to manage for a species, you can worry about the north-facing slopes, for example. And one other example I'm going to show, and this is the last example, and this is just some work we've done recently with Stu Weiss, who is a consultant, works for Decision, and he has developed some approaches to looking at degree days and using our information to look at this at a fine scale. So considerations for vines are the growing degree days, how much heat can accumulate over the season, the length of the growing season, it has to accumulate by a certain period of time before it starts raining again or it starts getting cold, and then water availability to be able to water the grapes. And the tools that we're using are downscale temperature and water deficit. and a Gladstone's algorithm that corrects degree day calculations for wine grapes that we've shown to be very useful. This is a weather station that we installed up at Pepperwood Foundation, a Pepperwood Preserve, as part of a network, and this has soil moisture measurements in it, and then air temperature and radiation and solar and wind speed and various things. So this is something that is illustrating that there are local monitoring capabilities that we can build on to then help assess our changes over time. Okay, so this is the mean ripening date on the basis of air temperature. The top one is the historical time, and what we're looking at is the ripening date for Pinot Noir and Chardonnay. They have to develop 1,250 degree days by the time they're ripe. And you can see that from the historical, 1971 to 2000, to the most recent decade, there are places where in most places, the ripening date has gotten earlier. So anybody here that grows grapes recognizes that that may not give enough time for the grapes to ripen adequately, to develop all the right characteristics. So it has increased. That means that sometimes there's going to be grape varieties that are going to have to be changed here. Now, if we go into the future, the top one is the 2009. That doesn't look right. Huh. Okay. In any case, the bottom one is the GFDLA2. Did I get those wrong? Let me go back. Oh, it doesn't look right. Okay, don't look at the top one. The bottom one is the 2020, I love this, 2025. So that's not very far in the future. That's the average of 2010 now and 2040. So as you're going into the future, we've gone up, and I'll show you the number of days forward for this particular variety. And this is the number of days in advance historically, just from historically to this decade, and then from this decade to the next 30 years. And so we've had increases in days of up to 20 days earlier that this particular variety, the locations that are suitable for it have now increased. So that's how much earlier they would have to be harvested. Just an example for Cabernet Sauvignon, the same thing. This is 1971 through 2000, and then the current, and we've already seen an increase in the ripening date, advancement in the ripening date. And if we go to the end, you can see that it's even more. Now this doesn't have as warm of colors because Cabernet Sauvignon is harvested later than Pinot Noir and Sauvignon Blanc. But you can see that it has had a large increase in ripening date advancement. So that's one way to look at those things. And one other example we are using for the Sonoma County Water Agency, doing a little project looking at water deficit to estimate agricultural demand. And here again this is the middle Russian River. And those colored areas are areas that actually have agricultural withdrawals. So the reduction between stream gauges from the north end of this little reach to the south end is channel loss. It's stream flow loss that is represented by agricultural demand. Oh, okay. I will whip right through this and give you my final, hello. Okay, take-home message. Climate change is changing, and spatial scale matters. Modeling approaches can address processes at multiple scales. It's not all gloom and doom because if you are acknowledging these processes at a fine enough scale, you can see habitat resiliency that can inform adaptation strategies, and providing an understanding of ongoing and potential changes can facilitate all kinds of planning. There is uncertainty in future projections, moderated by deterministic processes. There are manifested locally. There's less uncertainty in the direction of air temperature change, and climatic water deficit reflects increases regardless of the precipitation scenario. My final slide, climate change science is in its infancy. Advances in methods and computing technology are providing the ability to reduce uncertainty by embedding finer scale simulations within global climate models, and measurements of ongoing change at multiple scales can inform future models. And hydrologic tools are capable of informing decision makers of potential impacts of climate change for water availability, habitats, and agriculture.